Welcome to our deep dive into the fascinating world of transition metal. These elements, found in the central block of the periodic table, play a crucial role in both nature and technology. From their unique electronic configuration to their wide range of application, transition metals are truly the backbone of modern chemistry and industry. In this video, we'll explore their property, trends across the periodic table, and why they are so important in our daily lives. Let's begin by transition metals are typically defined as elements whose atoms have an incomplete d subshell, or which can give rise to cation with an incomplete d subshell. This unique electron configuration leads to a variety of interesting chemical behavior, such as variable oxidation state, colored compound, and the ability to form complex ions. These properties set them apart from S-block and P-block elements, making them a subject of intense study and practical use. Let's look close. Transition metals occupy the D block of the periodic table, spanning groups 3 to 12. This central location is significant because it bridges the highly reactive S-block metal on the left with the more varied P-block element on the right. The D block includes familiar metals like iron, copper, and gold, as well as less common ones such as ruthenium and osmium. Their placement is not just a matter of convenience, it reflects their shared electron configuration and similar. Defining feature of transition metal is their electronic configuration. Typically, they have a partially filled d subshell in either their neutral or ionized state. For example, iron has the configuration HR-S2-3D, while copper is HR-S1-3D. Thus, this arrangement allows for a range of oxidation states and contributes to their ability to form colored compounds and complex ions. Understanding these configurations is key to predicting their chemical. One of the most notable characteristics of transition metal is their ability to exhibit multiple oxidation states. Unlike S-block elements, which usually have a single common oxidation state, transition metal can lose different numbers of electrons depending on the chemical environment. For instance, iron can exist as Fe2+ or Fe3+, while manganese can range from +2 to +7. This versatility is crucial for their roles in catalysis and redox reactions. Transition metals are famous for forming vividly colored compounds. This is due to d-d electron transition, where electrons jump between different d orbitals, absorbing specific wavelengths of light. For example, potassium permanganate is deep purple, while copper sulfate is bright blue. These colors are not just visually striking, they are also useful in analytical chemistry and industrial processing. Another key property of transition metal is their ability to form complex ions. These are species where the metal ion is surrounded by molecules or ions called ligands. The flexibility of the d orbital allows transition metal to bond with a variety of ligands, leading to diverse structure and reactivity. Complex ions are central to many biological systems and industrial catalysts. Transition metals display interesting magnetic behavior. Compounds with unpaired d electrons are paramagnetic, meaning they are attracted to magnetic fields. Those with all paired electrons are diamagnetic and are slightly repelled. For example, iron is strongly magnetic due to its unpaired electron, while zinc, with a full d subshell, is not. These properties are important in both fundamental research and practical applications like data storage. Transition metals are widely used as catalysts in chemical reactions. Their ability to adopt multiple oxidation states and form complex ions makes them ideal for speeding up reaction without being consumed. For instance, iron is used in the Haber process for ammonia synthesis, while platinum is key in catalytic converters. This catalytic prowess is essential for many industrial and environmental processes. Transition metals are known for their high melting and boiling points, hardness, and good electrical and thermal conductivity. These physical properties stem from strong metallic bonding and the presence of delocalized d electrons. As a result, metals like iron, nickel, and copper are widely used in construction, electronics, and transportation. As we move across the transition series from left to right, certain trends become apparent. Atomic size generally decreases, while density and melting point often increase. The number of possible oxidation states also tends to rise and then fall. These trends are linked to the gradual filling of the d orbital and the increasing nuclear charge. Comparing S-block and D-block elements highlights the unique nature of transition metals. While S-block metals like sodium and potassium are highly reactive and soft, D-block metals are harder, less reactive, and have more complex chemistry. This difference is largely due to the involvement of d electrons in bonding and chemical reaction. D electrons in transition metal are responsible for many of their distinctive properties. These electrons can participate in bonding, leading to variable oxidation states and the formation of complex ions. They also contribute to the metallic luster, electrical conductivity, and magnetic properties that make these metals so valuable. Transition metals can form interstitial compounds when small atoms like carbon, nitrogen, or hydrogen occupy spaces within the metal lattice. These compounds are often harder and have higher melting points than the pure metal. For example, steel is an interstitial compound of iron and carbon, combining strength and durability for countless applications. Many transition metals form non-stoichiometric compounds, where the ratio of elements is not fixed. This occurs due to defects in the crystal lattice or variable oxidation states. These compounds often have unique electrical and magnetic properties, making them important in advanced materials science. Transition metals are renowned for their high melting and boiling points. This is due to the strong metallic bonds formed by delocalized d electrons. As a result, metals like tungsten and molybdenum can withstand extreme temperatures, making them essential in high-performance equipment and industrial processes. Transition metals are excellent conductors of electricity thanks to their delocalized electrons. Copper, for example, is widely used in electrical wiring due to its low resistance and high conductivity. This property is a direct result of their unique electronic structure and metallic bonding. In addition to electrical conductivity, transition metals also excel at conducting heat. This makes them ideal for use in cookware, heat exchangers, and engines. The efficient transfer of heat is another benefit of their metallic bonding and the presence of mobile electrons. Transition metals are both malleable and ductile, meaning they can be hammered into sheets or drawn into wires without breaking. This property is essential for manufacturing and construction, allowing metals like iron and copper to be shaped into countless forms for various uses. Transition metals are often used to create alloys, mixtures of metal that combine the best properties of each component. Steel, bronze, and brass are all alloys that rely on transition metals for strength, durability, and resistance to corrosion. These materials are foundational to modern infrastructure and technology. Some transition metals, such as iron, cobalt, and nickel, are ferromagnetic, meaning they can be permanently magnetized. This property is crucial for the production of magnets, electric motors, and data storage devices. The magnetic behavior arises from the alignment of unpaired d electrons within the metal lattice. Transition metals are at the heart of many catalytic processes, both in industry and nature. Their ability to change oxidation states and form complexes allows them to facilitate reactions that would otherwise be slow or impossible. Examples include the use of platinum in fuel cells and vanadium in the production of sulfuric acid. Transition metals are essential for life. Iron is a key component of hemoglobin, enabling oxygen transport in blood. Zinc is vital for enzyme function, while copper plays a role in electron transport chain. These metals are carefully regulated in biological systems to maintain health and support complex biochemical reactions. From construction to electronics, transition metals are indispensable in modern industry. Steel structures, copper wiring, and platinum catalysts are just a few examples of how these elements support technological advancement. The unique combination of strength, conductivity, and reactivity makes them irreplaceable in countless applications. While transition metals are vital for industry, their extraction and use can have significant environmental impact. Mining and refining processes can lead to pollution and habitat destruction. However, advances in recycling and green chemistry are helping to reduce these effects and promote sustainable use of these valuable resources. Beyond the main transition metals, the lanthanides and actinides are sometimes considered in a transition metal. These elements, found in the F block, have their own unique properties, such as strong magnetic behavior and radioactive decay. They are important in specialized applications like nuclear energy and advanced electronics. Coordination chemistry is a major field of study involving transition metals. Here, metal ions bind to groups of ligands, forming coordination complexes with diverse structure and reactivity. These complexes are central to many biological processes and industrial catalysts, highlighting the versatility of transition metals. Crystal field theory helps explain the color, magnetism, and stability of transition metal complexes. It describes how the arrangement of ligands around a metal ion splits the d orbital energy, leading to various observable properties. This theory is fundamental to understanding the behavior of transition metal compounds. Jahn-Teller effect is a phenomenon observed in some transition metal complexes, where geometric distortion occurs to lower the energy of the system. This effect influences the stability, color, and magnetic properties of complexes and is an important consideration in coordination chemistry. Spectrochemical theory ranks ligands based on their ability to split d orbital energy in transition metal complexes. Strong field ligands like cyanide cause large splitting, leading to low spin complexes, while weak field ligands like iodide result in high spin complexes. This theory is key to predicting the properties of coordination compounds. Chelation occurs when a ligand forms multiple bonds to a single metal ion, creating a ring structure. Chelating agents greatly increase the stability of complexes, which is why they are used in medicine, water treatment, and analytical chemistry. The chelate effect is a cornerstone of coordination chemistry. Transition metals are all around us, from the steel in our buildings to the copper in our electronics. Even the coins in your pocket and the jewelry you wear likely contain transition metals. Their unique combination of properties ensures they remain essential to modern society. Transition metals play a vital role in medicine. Platinum compounds are used in chemotherapy, while iron supplements treat anemia. Imaging agents containing gadolinium help doctors visualize internal organs. The versatility of these metals continues to drive innovation in healthcare. Transition metals are involved in many environmental processes, both beneficial and harmful. They can act as catalysts in breaking down pollutants, but can also accumulate as toxic contaminants. Understanding their chemistry is key to managing their impact on the environment. Transition metals are central to energy technology. They are used in batteries, fuel cells, and solar panels, enabling efficient energy storage and conversion. Their unique properties make them indispensable in the quest for sustainable energy solutions. Throughout history, transition metals have been prized for their beauty and utility. Gold and silver have been used for coins and jewelry, while copper and iron have shaped tools and weapons. Their impact on art, culture, and civilization is profound and enduring. Modern technology relies heavily on transition metals. From the microchips in computers to the magnets in electric vehicles, these elements are at the heart of innovation. Their unique combination of strength, conductivity, and reactivity drives progress in countless fields. As technology advances, the demand for transition metal continues to grow. Research is focused on finding new sources, improving recycling, and developing alternatives to reduce environmental impact. The future of transition metal is closely tied to the future of technology and sustainability. Recap: transition metals are defined by their incomplete d subshell, variable oxidation states, and ability to form complex ions. They are hard, conductive, and often magnetic, with a wide range of colors and reactivity. These properties make them essential in science, industry, and daily life. Across the periodic table, transition metals show clear trends in atomic size, density, and oxidation states. Their unique position and electron configuration explain their diverse and valuable properties. Understanding these trends helps chemists predict and harness their behavior. Innovation in materials, science, energy, and medicine often depends on transition metals. Their versatility and unique properties enable breakthroughs in technology and sustainability. As we continue to explore their potential, transition metals will remain at the forefront of scientific progress. Despite their many benefits, transition metals present challenges such as resource scarcity and environmental impact. Addressing these issues requires innovation in extraction, recycling, and alternative materials. The opportunities for sustainable development are vast, and ongoing research is key. Learning about transition metals is a cornerstone of chemistry education. Their diverse properties and applications provide a rich context for understanding atomic structure, bonding, and reactivity. Mastery of this topic opens doors to advanced study and careers in science and engineering. In summary, transition metals are a group of elements with remarkable properties and wide-ranging applications. Their unique chemistry underpins much of modern technology and industry. By understanding their behavior, we can better appreciate their role in shaping our world and look forward to new discovery. As we look to the future, transition metals will continue to be at the heart of scientific and technological progress. Whether in new materials, energy solutions, or medical breakthroughs, their versatility ensures they remain indispensable. Stay curious and keep exploring the amazing world of transition metals.